join them in so-called cobra weave. When such chain has one of its entities, it rapidly dislodges wavefront travels through the chain. We are investigating this phenomenon. The chain must be weaved in a manner as you can see in the picture. When one of these sticks is released, the wave travels through the chain. It is important to note this angle theta, which will be important nextly in our presentation. Also, when we pull the green stick, it is not equivalent to the red stick, and with the pulling of the green stick, the cobra phenomenon occurs, as can be seen here in the video. While when we put on the red stick, it just bounces off the ground and explodes in this manner. We will be concentrating on the green stick phenomenon. This one occurs because when the green stick is released, the cobra rises as the sticks get expelled downwards, as you can see in the diagram here. The sticks, as they get expelled downwards, they impart a recoil onto the end of the cobra, rising it. Another forces that are acting on the end of the cobra is the elasticity of the cobra as we bend it, and also there is the gravitational pull onto the cobra. We will be in the first part of our presentation concentrating on the height of the cobra, which is defined in the place where the sticks are not part of the weave anymore. In the beginning of the phenomenon, as the time increases, we see cobra rising, and it gradually enters the steady state. We can see that this indeed happens, and nothing else. As the cobra rises in this measurement of a 7-meter long cobra, we can see that there is observable height limit. In the steady state, the height of the cobra may look something like this, and we can see this from the stable equilibrium of the forces we have shown before. There is also sometimes an oscillatory movement, which is the result of the dynamical equilibrium of these forces. Let us move on to the theoretical account, which in the beginning we will in the beginning be focusing on the elastic potential energy of the sticks. This depends on the dimensions of the stick and the radius of curvature of the stick in the weave. In first approximation, we will demand that the potential energy will be equal to the elastic potential energy. The potential energy in the gravitational field will be equal to elastic potential energy, arriving at this formula. We can, from this, estimate the height, but we need to note that this expression will be extremely sensitive to the quantity r, the radius of curvature. With this, we need to determine a method. We need to define a method of determining the radius of curvature, which we will do geometrically using the GeoGebra, obtaining the radius of curvature accurately. Also, in the formula I have shown you before, there is the Young's modulus, and we will not be using the table values, but rather we will measure it. With this simple formula, it can be defined and measured for one stick, and for this particular stick it is obtained this value, and in the cobra we measure several sticks to obtain the average Young's modulus. So, with this formula, when we compare it with the height that it tends to reach, in steady state we get a clear overestimate. This should make sense because there will be indeed more energies in play, such as are the potential energies and the rotational energies imparted on the sticks when they leave the cobra. From this, indeed, we can arrive at the correct model for the height, which involves also the such, but we will see that, and we see that it correlates with our measurements. Here you can see five measurements of the same cobra correlated with it, but it's extremely problematic to obtain all the data such as anti-rotations, so we will see a better theoretical model. Firstly, we will check the literature, and we will see that they indeed can determine the cobra height based on such expression, where this is the curvature of the cobra, but this would require solving third order or ODE. So we will get inspired by this because they obtain this from forces. So we will get inspired and we will study the forces as well. Firstly, there is the recoil forces, the elastic and the gravitational forces, as we mentioned in the beginning. We will focus now on the recoil force, which will have direction opposite to the sticks leaving the cobra and can be defined as this, where the m is mass of one obstacle, vt is the terminal obstacle's velocity, and frequency is the frequency of departures, f. And then there will be another force, which will be acting perpendicular on the end of the cobra, and that is the elastic force, which is dependent on the Young's modulus, the displacement of the free end, and the dimensions of the sticks. With this, finally, we will focus on the gravitational force, which is this rather daunting formula. But we will see that there enters the length of the cobra and the linear mass density from which this complicated term comes from. It is from studying the geometry of the setup. We will demand the balance of forces and arrive at such formula for the height. When we compare this with our experiments, this formula is dependent on the geometry of the cobra through the angle theta I mentioned in the beginning. So when we look at the dependence on the angle theta, we arrive at a good correlation for the different thetas. And then we can change also the width of the cobra, which also affects the formula I have displayed, and we arrive at correlation. Next thing we be concentrating on is the wave velocity. Indeed, the cobra in the steady states travels at a steady velocity. The theory for this is analyzed in the literature, arriving at this formula. This formula is gives us the idea how the velocity scales with different parameters. We need to note that this function is a dimensionless factor that depends on the geometry of the whole cobra. We will estimate it to scale as cosine. Well, so from the experiment, we will be able to determine the velocity, as you can see it indeed is the steady state velocity, and we will see that it scales as we predict. And for the specific sticks they used in this article, we arrive at psi equal to 3.95, as well as they do in the article. So, moving on to our own sticks, we estimated the psi to be to scale as cosine of theta. So we can see that. So why is it that we estimated is as such is that with small theta that there will be a less dense cobra. So with one expelled stick, the travel distance is greater for this cobra and therefore the velocity should scale with cosine. Indeed, when we plug in cosine, we get such a trend here, correlating with what we thought. Next, what we will be investigating is the effective length of the cobra, of the sticks woven into the cobra, which also affects the velocity, and we can see that indeed the velocity scales as 1 over L squared, as you can see in the picture here. So, to summarize, what we did was we presented the cobra as it as we should create it. We presented qualitative theory based on potential energies, and then we corrected it with the forces, as you can see here. Then we are investigating the effect of changing angle and width on the height of the cobra, and moreover we presented theory taken from an article for the angle and length as it affects the wave, the velocity of wave propagating through the cobra. I would like to thank you for your attention.
2 minutes time for questions from the audience.
Just want to quickly please open file number 45, and while opening, could answer the question, what's the nature of
45?
45 here. What's the wave that travels along the cobra? What is the wave?
The wave is...
The wave of what? What's the wave? Elastic maybe, or...
Well, it is... it is elastic deformation that travels.
I got it. On this frame, I see that there are different sticks. So are you sure that the models of right and left and right and left pitches are the same?
These sticks are precisely the same. The only thing that was changed was the density.
If the Young modulus is the same.
Well, for these sticks, yes.
I got it. So now please. So you use lots of literature in your mathematical models. Can you show? Are you sure that all basic equations that are used in the series are the same? For example, potential energy deformation, we use it. Are you sure that in all papers that you used, this equation was the same? For potential energy deformation for the cobra?
No.
Yes, no?
No.
I got it, thank you. So what's the most important parameters for the surface in your opinion? The surface. The surface,
What's
the main important parameters for the surface?
There is this parameter called second moment of the surface that affects this phenomenon. That's where we were.
Friction, maybe.
Well, we were assuming that it is the friction.
I will discuss it later. Finally, can you observe the phenomenon with all the parameters of the cobra? So are there some boundary conditions for maybe some geometry?
Yes, of course. There is.
And now slide number 7, please. I'm sure that elastic force has the correct direction on the frame. Yes or no?
Sorry, time's up. You got to postpone that.
Well, it all be
Sorry.
to the cobra.
Can you please proceed preparing the answers?
17, and I'm happy to present our position of round number 17 for cycle generation. Let's go to the main results of this report. There was an energy conservation model for kinetic phenomenon. It was told that potential energy transformation of the stick goes into kinetic energy that you have for forward and rotation component, and the potential energy of gravity. I agree with it, but not at all. Of course, there are some energy losses, for example, friction between the sticks, friction between the floor, air resistance, and also oscillation of the cover. That can be very important since, because of human factor on control, and if it is in control, cover can oscillate in the perpendicular direction of its motion. After it was also a explanation based of force balance. I agree with it. It's okay in my opinion. After it was a split of the front investigation, but it was a model that mostly based on the papers. So it's not so strong point for this report. After it was told about the head of the cover, it also was mostly cited of the papers and just comparing a few operations from the papers to one big and comparing it with the experiment. So it isn't so good in my opinion. Also, it was basic how the geometry of the cobra can change the phenomenon. It was an investigation for angle between the sticks, this one, and how the lens changes. But I'm not sure that really in experiments with different planes, young modulus and point ratio were the same because it wasn't proved. So the main strong points of the review were positive explanation of stick rising, of why height of the cobra is constant. It was because of the force balance. They were all forces acting on the cobra. It was investigation, not full, but it was primitive investigation for height and velocity of the cobra. And for example, lessons of the sticks was to change. If you talk about the not so strong points of the report, for example, it was that role of the surface wasn't investigated at all. In my opinion, role of the surface is one of the main important parameters that can affect the height of the cover. We'll discuss it on the we'll talk about it on the discussion. It was not so mostly theory was put from the papers. That isn't so good because if you look, for example, because this problem was played previous year on student phenomenon. If we see the equation he had in beginning. Lots of them were in Greece team paper publicated after the tournament. Its name is Kasaros. You can check it if you want. And human factor experiment wasn't good effect. So if there was a task fulfillment, what can we see? We were asked to create a cobra, yes, it was done. The motion of the front, yes, it was observed. But after investigation, it was not full. For example, it was mostly checking the papers, and it wasn't some novelty and something from the reporter. So now I'm